Hello, I'm Franck Poitrasson from the Geoscience Environment Laboratory in Toulouse, and I'm going to give you a lecture on why is it important to perform long-term monitoring of the Amazon Basin rivers in the framework of this Curso Fluvius Havaianas lecture series. But the first question maybe is why the Amazon River Basin? As you all know, this is because of its importance. It is of global importance. This is the largest river in the world, and therefore it delivers 17% of the fresh water delivered to the global oceans. It delivers also, of course, a lot of suspended matter, mineral nutrients, and so on and so forth. And therefore, this basin has a key importance on continent-ocean transfer. Another key property of this continental scale Amazon River Basin is that it nearly matches the Amazon biome. You see the Amazon River watershed limits represented by the blue line here, and the Amazon biome limits represented by the white lines here. And this Amazon biome is very important as well because this is the largest tropical forest in the world. It hosts a lot of biodiversity, particularly at the footsteps of the Andes on the west here. And this Amazon forest has been for a long time a sink of greenhouse gases. It has been a sink for CO2, atmospheric CO2, but the thing have changed at the turn of the century since during the major drought of 2005 and 2010, this forest has turned into a source. And some climatologists say that during this century, the Amazon forest may turn as a permanent source of CO2, with the forest turning into a savanna. Of major concern is the deforestation affecting the Amazon forests, particularly strong in the deforestation arc shown in red here in this map. And current estimate considered that about 20% of the forest has already gone. And some climatologists say that if you reach a threshold of 25%, you may reach the tipping point I was mentioning, where the tropical rainforest will turn into a savanna. And therefore, it is important to monitor the evolution of this forest, and monitoring the rivers of the Amazon Basin would be a good way to see how things are evolving and to understand the mechanism at play, as I'm going to show you during this lecture by several examples. This is the sad things of the story, but you can take a more positive view in saying that if we lost 20%, we still have 80% of the forest that is still there, as shown by the green area. And compared to other tropical forests elsewhere in the world, such as the Indonesian forest, where 80% of the forest has been transformed into palm trees to produce oil, then this indicates that the Amazon forest is still a good place to study a natural and preserved rainforest. Hence the reason to study the Amazon River Basin and biome, which is relatively better preserved from human activity relative to other tropical forests elsewhere in the world. Yet it doesn't mean that the Amazon Basin is devoid of the major climatic change that is affecting the Earth at the moment. Like anywhere else in the world, the Amazon Basin is impacted by more extreme and intense climatic events. Here we can see pictures taken from the French news that concern the huge drought that is affecting the area of Manaus, as you are experiencing at the moment. So we can see the impact this has on the people living near the river with the floating houses and the impact it should have as well on the fishing. This obviously has a strong impact on the supply for drinking water, and of course this has also a strong impact on navigation for the transport of people and the goods. So for those extreme events as well, we need to carry out monitoring of the Amazon River Basin. So the objective of the lecture is to illustrate the importance of a research program involving the long-term monitoring of the Amazon Basin rivers. So I will focus on monitoring of the water level and river discharge. Then I will continue on the suspended sediment load monitoring. And then I will end with the water chemistry monitoring that is progressively increasing. And the end of the lecture will be dedicated with example of anthropic impact on rivers concerning dam construction, gold mining, and particularly illegal gold mining, as well as oil extraction. And on the last two examples, I will give you a view on the impact of environmental policies and what this does in terms of remediation. So the first parameter that is monitored since a long time, since it is monitored since 1902 in the port of Manaus. This is the water level, and you can see here the maximum water level of the Negro River in the port of Manaus. You see here the maximum value that was reached in 2021. It was extremely high, and you may fear that if this continues, maybe the restaurant will become flooded, unfortunately. With this compilation by Marango et al., you can see that the minimum level of the water at Manaus shows very well the drought, the major drought, represented by vertical dashed lines here, and you can particularly see the major drought of 2005 and 2010 I was mentioning. So this shows very well the drought over the last 110 years. So I've got to hide there to show you in full this more comprehensive and more recent compilation by Espinosa and co-workers. So the red lines here show you the same feature that I was showing before, which is the minimum water levels, except that here you've got the absolute measurement in meters, and you can see again the drought of 2005-2010 seen by minimum water levels value. But here you've got also the maximum water level values that represent the floods, and you can easily see here that in the last 20 years you have an increase of the flooding events, which translate into an increase into the amplitude between the minimum and the maximum value over the last 20 years. This is also well shown by this graph here, showing the maximum water levels, and you can see that for the recent floods, the curve tends to be above the others for a long amount of time. This is true for 2021 or 2009, for example. And this is another way, again, to show this evolution and the fact that we have more and more extreme events, which is the duration of the emergency situations in days. And you can see that by the last 10 or 20 years, we've got an increase of these emergency situations, with which also become longer. The 2021 was particularly long. So all to say that this compilation shows very well that the simple monitoring of the water level of the Negro River, it shows that the floods, the drought increase in intensity, duration, and frequency over the last 20 years. So let's move from Manaus here to Óbidos here in green, which is an interesting point because this is the last HIBAM or ANA Gojin Station before the influence of the ocean tide. So the hydrologists particularly like this point. And this is because here now I'm no longer talking about the level of the river, but about the discharge of the Amazon River. And hydrologists can translate one into the other by doing making rating curves that allow them to say for a given level of water you would have a certain water discharge. And in doing so, Glor and co-workers could see the minimum monthly means, here again for the water discharge at Obidos, and they showed that this translates very well again into this shows very well the drought, but with the annual mean and the maximum monthly mean, you can see an increase into the water discharge over the last 20 years. And the interesting thing is that this correlates with the Amazon basin precipitation over the last 20 years. And the Amazon rainfall over the 2001-2009 period particularly increased in the northwest of the Amazon basin compared to the 1981 to 1919 period. Another parameter to which those increases in the water discharge correlate is the sea surface temperature of the tropical Atlantic Ocean. You can see this increase. And therefore, this leads Glor et al. To explain that this increase in the water discharge over the last 20 years is a climatic effect in response of the increase of the water basin rainfall, which is itself related to the sea surface temperature of the tropical ocean. So I can reappear now to show you the next parameter that is being increasingly monitored into the Amazon River basin, which is the amount of suspended matter that is in the water. That can be easily seen in this classical example of the mixing between the Negro River in black and the Solimoes River in white. You've got the Negro River in black that is very poor in suspended material, and the Solimoes River, the white water, that is very enriched in suspended material. And you can see this very easily from this picture taken from a boat. But the interesting thing is that you can also very easily see from this from satellite images. As you can see here, you've got the Negro, here you've got the Solimoes. This is the city of Manaus. And therefore, you can imagine that with the proper calibration, you can, from remote sensing, obtain an estimate of the amount of suspended matter, at least at the surface of the rivers. And this is what I'm going to illustrate with the example of the Purus River, which is known to be a black or white river, depending on the season. Here you've got the watershed of the Purus River, which is close to the center of the Amazon basin. And in this work by Martinelli et al., they show the relationship between precipitation, the gray bar, and the water discharge. You can see a slight shift between precipitation maximum and water discharge maximum, which is probably related to the response of the system and the flowing of the water. Martinelli et al. Did a very careful work in which they tried to compare field data with remote sensing data. The field data are represented by the white dots. So the field data imply that you go to the field with a boat, you do the sampling, you do filtration, you weigh the sample to estimate the amount of suspended matter in the water, whereas with the remote sensing, after proper calibration, of course, then you directly obtain the amount of the suspended matter at the surface of the water. These are the black dots, and you can see in this time series going from June 2010 to June 2015, you have a very good match between the field data, the white dots, and the remote sensing data, the black dots. So the good thing is that they had store all the satellite images, and therefore, thanks to that, they could go back into the past, which is something you cannot do by fieldwork. If you didn't take the sample at the right time, that you cannot do this. So the dashed inset here represent this period, 10 to 15, and here they could go all the way to the year 2000 and show that what they found during this period was occurring before already. And there are two key and interesting information that you could derive from this detailed study. The first thing is that if you would do a few field work, then it's very likely that you wouldn't obtain sample representative of the whole dynamic of the system. For example, it's very likely that you would mostly miss the peak in the suspended sediment discharge. And the second important information that was gained from this work is that half of the suspended sediment load is carried in only 2 months, which are mostly January and February, which is very specific to the Purus River, because in other rivers in the Amazon Basin, the period during which the larger quantity of the suspended matter is carried is wider, and this therefore may explain why the Purus is black for most of the time, but sometimes turns white for a short period of time. In this earlier work by Martinez and co-workers, this time again at Óbidos, at the station of Óbidos, they compared the average discharge, again the gray bars, with the river suspended sediment discharge, the black dots, and they found that whereas the river discharge, despite the scatter, remained mostly constant over the period considered, which is 1996 to 2007, then they show a progressive increase in the river suspended discharge. But the next point was then how to explain this, how to interpret this. So they put two different hypotheses. One possibility is that this is related to land cover change upstream, maybe related to deforestation, which would enhance erosion and as a result an increasing amount of suspended sediment in the waters. Or another possible interpretation was that this was the result of climate change with more frequent extreme storm events that would be accompanied by increased erosion. So this question was investigated further by Armijos and co-workers, and this time they separated the sediment fraction into two different sizes. There is the coarse fraction, which is in gray here, that represent the sediment that are bigger than 63 microns, and the fine suspended sediment load, that is the fraction between 63 microns and 0.45 microns. And the interesting thing is that depending on the year, you can see that the maximum values are shifted. The fine fraction happens at the beginning of the year, whereas the coarse fraction rather happens in the middle of the year, around June, July. And the other interesting result obtained in this work is that they found that the fine fraction was related to the rainfall over the Amazon basin, whereas the coarse fraction was rather related to the water discharge in the Óbidos station. So the interpretation by Armijos et al. Is that the coarse sediment load evolution monitored discharge in the floodplain before the Óbidos station, whereas the fine fraction would rather monitor the rainfall regime in the Andes much further upstream. So you can see that in separating and monitoring two different size fractions of the suspended sediment, then you can make inference about two different mechanisms affecting the Amazon basin. So let's look now at the last parameter that I would like to discuss during this lecture, which is the monitoring of river chemistry. So this is a parameter that is more complicated to monitor relative to the previous one, because you need a lot of time and people time, and as shown, for example, by the HIBAM observatory that monitor the Amazon Basin river chemistry since more than 20 years, but this requires a lot of workforce for that. And the reason is that you need to go to the center of the river to sample the water. If you have to go far, you have to go through big boats. And you can do surface water sampling, you can do depth water sampling. Once you sample your sample, you do physical and chemical measurements to measure the pH, conductivity, temperature. Then you will want to do filtration to measure the suspended and the dissolved chemical composition of the water. And you may even want to do more sophisticated filtration if you want finer, have an idea of the colloidal fraction, for example. And once you've sampled and filtered your sample, you have to store them properly all the way to the lab to do chemical analysis through spectroscopy and mass spectrometries, which is again time and expensive. But since some time, we increasingly see the use of those multiparametric probes, which besides the pH, conductivity, and redox can give you a continuous monitoring of the chemical composition of the river, such as the nitrate, the chloride, or even the dissolved organic carbon, as I'm going to show you on the basis of the following example. Maybe we should we should go one step back to see what is the context of this question of the carbon cycling in tropical forest. So this is based on the reading of the 2019 IPCC report on climate change and lands. There are many uncertainties about the carbon cycling in the tropical forests. For example, the carbon flux from those tropical forests to the ocean might be underestimated by 70% according to some, and therefore it would then represent 10% of the anthropic greenhouse gas emission. So then this would really become something significant. There is also a highly variable atmospheric carbon flux from tropical forests due to the fact that this is difficult to estimate from remote sensing, and that moreover do not take into account ground flux. They mostly monitor the flux coming out from the canopy. And the role of tropical forest on carbon storage is uncertain. And this is notably because the wet zones are poorly known. They are poorly known in terms of their actual extension, but also in terms of their functioning. For example, for the mineralization of the organic matter, the function of the iron reduction through times, or bacterial activity that remains debated in the community. And for that, most of these works were lab work or computational work. For that, we need to do fieldwork monitoring. Just an illustration of the unknown regarding the carbon cycle. This is a compilation of 7 climatic models, and you can see that compared to the high latitude, the low latitude between the tropics, the uncertainty is very large for the carbon release or the carbon uptake, as you can see here. And the result is that when you want to do a prediction for the future, then you rapidly have a large uncertainty into the cycling of this carbon, and therefore we really need to go back to the field and see what's going on in tropical forests. And this is what our colleagues from INPA did in this biological reserve located 60 kilometers north of Manaus in the Cuiras Reserve. This is the location of this reserve. and they monitored what was the carbon cycling in the Azu stream, which is a first order stream. And so you can see here the cross section with the wells to monitor the groundwater levels. And this is a field picture of the site. You see the path to go where. This is the Azu River. And near the river, you've got this frame here that allowed Montero and co-workers to install automated equipment to monitor the water level and therefore the water discharge, but also other physical and chemical parameters thanks to the multi-parametric probe I showed you before. And with this equipment, they first tried to see what was the impact of storms on those physical and chemical parameters of the waters. And for example, in this storm, you can see that you have an increase in the water discharge due to the storm, which is correlated with an increase of the electrical conductivity of the river water, as well as with an increase of the dissolved organic carbon. Another storm event showed the same parameter. You see an increase of the electrical conductivity under dock with the water discharge, but with a much more intense event. You can see here that the discharge was 10 to 20 times stronger than what it was in these two events. Then the response is totally different. Instead, you see a very slight increase into the electrical conductivity and the dissolved organic carbon content. But this time you've got a very strong response to the pH, going to a higher value than usual for those black waters. And the interpretation of Montero et al. Is that this was related to a different way the water went from the surface of the soil to the stream. In here, the water percolated the soil, went through the groundwater, collected the dissolved organic matter, and went to the river. Whereas here, you essentially had a runoff of the water at the surface of the soil that went directly into the stream water, and therefore this increase into the pH with little impact on the electrical conductivity and dissolved organic carbon that is mostly located into the groundwater. The next step in this study is to see how those signals from first order stream translate into the bigger rivers that will collect all those water from the first order streams. And for example, Montero et al. Here show the data they've collected at the scale of 1 year. So the discharge, the dissolved organic carbon, electrical conductivity, that match very well. And you see here the precipitations with the arrows showing the daily event that we've looked at in the previous slide. And the striking thing here is that if you look at, for example, the discharge at the scale of 1 year, it doesn't correspond at all to the discharge evolution seen in the Rio Negro, for example, at Serinia, as monitored by the HIBAM observatory. And therefore, if you really want to understand and integrate this at the scale of the Amazon basin, you have to understand the transfer function of all those parameters from the first order stream to the big rivers to really be able to make inferences at the scale of the Amazon basin. So let's move now towards the end of this lecture with example of anthropic impact on rivers as monitored by the various approach I described before. And I will focus on dam construction. We'll give example of gold mining, then oil extraction, and see what the environmental policy permitted. So dams. There are many expected environmental impacts from dams. Upstream, you may have an increase of fish yield, greenhouse gas emission, mercury contamination, and downstream, people consider that you will have a decrease in the sediment supply, nutrient supply, an increase in greenhouse gas emission and mercury contamination as well, a decrease in the food pulse, as well as a decrease in the fish yield. And I will show you some of these parameters after that. And I will illustrate this with the example of the Balbina Dam that was built in 1987 on the Guatemala River, north of the city of Manaus. This is the Balbina Dam. Manaus should be around here. This is an expanded view of the reservoir created by the dam with the gauging station downstream, the Guatemala River. And this gauging station show the impact of the water discharge and therefore the average stage height of the river before and after dam construction. Before dam construction, you had a large amplitude of the water level, and after dam construction, then you had a much narrower range of water level, which is good if you want to build houses or install villages. But this is not so good for fishing because it has been shown that the fish yield depend on the proportion of inundated surfaces. Another parameter that was monitored by Forsberg et al. Was the quantity of mercury present in fish during a period of about 10 years, in blue here, as well as the quantity of mercury present in people hair, local people hair. And you can see that after the impoundment of the dam that occurred in 1987, then you see an increase in the fish mercury content as well as an increase in the people hair mercury content. Fortunately, those levels decreased after about 10 years. And the interpretation for this is that upon dam impoundment, the vegetation that was flooded was degraded by under anoxic condition, and this favored in the mercury cycle the methyl mercury forms. And after the full degradation of this vegetation, then you return to a normal natural mercury cycle. This is apparently not related at all to other activities such as gold mining. And the issues there is that those mercury value in fish, flesh as well as in people hair temporarily exceeded the maximum sanitary recommendation. Here the blue dashed line for the fish mercury content and the red dashed line for the people hair mercury content. So this was potentially at risk for the local people. The last thing I would like to show and illustrate here with those results is that this is difficult to do chemical monitoring, and therefore you cannot gain a lot of points. And for sure, if we could have had a method that would allow us to obtain more data, then we could have a better grasp of the dynamic of the mercury contamination and therefore a better understanding of the mechanism at play. But that's probably for the future. Next example concern gold mining of the Amazon basin, because the northern border of the Amazon basin is just here at the southern limit of the French Guiana. And we're going to look at the waters and the suspended matter in the Maroni River here, which is at the border between the French Guiana and Suriname, and the Oyapock River, which is at the border between French Guiana and Brazil. And on those maps here, you see the evolution of the surfaces impacted by illegal and legal, but mostly illegal gold mining. And the more you go towards orange or red colors, the more the surface area has been impacted by gold mining. So you see that on the Maroni River, from the year 2000 to the year 2014, you see an increase in the illegal gold mining, whereas for the other side, with the Oyapock River, you've got an increase from 2000 to 2008, but then a slight decrease going to the year 2014. And this is this increase in the Maroni River is well monitored by the daily surface suspended sediment obtained by Galley and co-workers over a period of 15 years. You can see this increase despite the scatter in different stations, Gojin stations here. And this can be illustrated in a different way by showing the sediment yield, so in terms per square kilometer per year, represented by the white squares here that show a progressive increase over the year, whereas the annual runoff in liter per second per square kilometer per year is scattered but doesn't show such a strong increase. And as a result, the cumulative sediment yield progressively increase more than the cumulative runoff, hence the deviation from this straight line. For the Oyapock River, the story is different, and you can see here with the cumulative curve that you tend to have a relative decrease of the sediment yield relative to the cumulative runoff, since we are below this straight line here. So we see an opposite relation between the Oyapock on the top and the Maroni rivers at the bottom. In this slide, we can see the relationship between the suspended sediment yield being monitored by Galley et al. With the evolution of the surface affected by mining as well as by agriculture. And in the Oyapock Basin, you can see that the gray dot shows a decrease in the mining area surfaces. But you also have a slight increase into the agricultured lands, which translate into a slight increase in the sediment yield, the white squares. For the Maroni, the picture is different. You have a strong increase in the surface affected by gold mining, as well as an increase of the surface affected by agriculture, which translate into an increase into the suspended sedimental yield as monitored by this study. And this result is interesting because this shows the difference of policies that was applied on the two watersheds. The Oyapock is at the border between French Guiana and Brazil enforced the prohibition of illegal gold mining, and you see the results, which is very important for the local people because this illegal gold mining is also associated with the strong use of mercury that is found in people, fish that they eat, and people hair. Whereas for the Maroni, the Suriname legalized the gold mining, and therefore this enhanced the impact of gold mining in the environment. And in between, the French Guiana was mostly dependent on the policy of its neighbors, it seems. The last example of this lecture concerns oil extraction and the impact this may have on the environment. If not properly done, if not done in a clean ways, it can release a lot of dangerous product in the environment because the deep waters that are associated with the oil in the reservoir contain a lot of heavy metal and polycyclic, polyaromatic hydrocarbons. And if this water is drunk by the people, like the local people, this can be at risk for their health. So this activity was investigated by Moke et al. In the foreland of the Andes here. This was based on petroleum concessions located in the equator here, the dotted area, as well as in Peru, the border between the two countries is here. And this was based on the monitoring of the El Tigre River here. And you can see in the red dotted limits representing the watershed of the El Tigre area. This is in, as I mentioned, in the foreland of the Andes. And in monitoring the rivers, so they monitored the discharge in blue, the conductivity here, the dark points, as well as the chlorine and sodium concentration. So you see that there is scatter, but the important point to notice is that at the beginning of 2009, you have a strong decrease in the water conductivity as well as in terms of the chlorine and sodium concentration. And this can be seen better here with this expansion of the graph. And actually this corresponded to the application of the Peruvian rule that prohibited deep water release without prior treatment. And you can see that this rule that was published in 2006 was put in operation 3 years later, as shown by the monitoring of the waters. A better way to see this is with the monitoring of the chlorine concentration in this log diagram. And you can see that in 2009, the El Tigre waters went down in terms of the chlorine concentration to the Purus River, which chlorine essentially comes from the rainwater. Another way to see it is to look at the sodium over chlorine ratio of the waters. Here you've got the El Tigre waters before the deep water release to the river was treated. So you essentially have a sodium over chlorine ratio of 1. Whereas here the squares, the red squares, correspond to the water of the El Tigre after the deep water were treated. And you can see that this sodium over chlorine ratio was below 1. So a ratio of 1 also corresponds to natural rivers that drain salt diapirs that occur in the Andes here, such as in this Hualaga River here. But after treatment, then you go back to the sodium over chlorine ratio of the Purus or other rivers, local rivers. So again, you can see that the monitoring was very good at seeing when a rule was put in operation regarding the petroleum extraction and treatment of the released water. So this is the end of this lecture, and time to make a summary of what we've discussed. The first point is that the Amazon Basin is of global importance for freshwater, biogeochemical flux as a source of biodiversity, for climate change, and also for the million of people living in it. So for this reason, it deserves our attention, no doubt about it. We've seen that it shows increasing departure from its normal natural cycles. I've shown many examples on this, and for this reason, this should be monitored. And rivers provide a good integrative view of the change going on in this complex system that the Amazon Basin River and the Amazon biome is. And besides the long-term water level monitoring, there has been an increasing survey of suspended sediments and water chemistry, and this can be aided by a modern approach using remote sensing and automated physical chemical probe, as we've seen. These approaches allow to monitor the effect of climate change, dam construction. We've seen also the effect of deforestation linked with illegal gold mining and oil extraction. Those monitoring approaches are also essential to observe the effect of local actions taken against illegal exploitation of the resource and on preservation policies, as we've seen. This last slide is just to show you The references I used to prepare this lecture, if you want to have a better and more detailed insight of the thing we've discussed. And if you had questions or comments, please feel free to email me here, and I will be happy to answer. Thank you.